Throughout the course of organic chemistry, you will be asked to evaluate the outcomes of many reactions. Your ability to predict the product of a reaction will depend on how well you understand the reactivity of the functional group in your molecules, how familiar you are with the mechanism of the reaction, how well you keep track of the atoms in your reactants and products, and how aware you are of the possible outcomes of a reaction. This tutorial will guide you through this process, with a particular emphasis on the regiochemistry and stereochemistry of a reaction. A reaction can be presented in many ways. For example, all the reactants could be placed to the left of the arrow. A solvent or other reaction condition may be indicated above or below the arrow. One of the reagents might be placed above or below the arrow. More than one set of reagents might be placed above or below the arrow to indicate two separate reactions. We will need to be attentive to these different ways of representing a reaction and realize that they really have many things in common. For example, most will have some sort of organic compound as a reactant. Most will also have some sort of reagent, and oftentimes a solvent will be indicated. Let's use an actual reaction as an example. The equation shown here represents the reaction of an organic compound with hydrochloric acid. Since the acid is used in its gaseous form, no solvent is used in this reaction. In predicting the product of this reaction, we need to identify the functional group in our organic reactant, which in this case is an alkene. Recall that alkenes act as Lewis bases and use their pi bond to attack electrophiles. When approaching any reaction, we should be wary of multiple outcomes and any preferences that a molecule might have for one outcome over the other. Regiochemistry often plays a role in organic reactions. Regiochemistry refers to the direction of bond making or bond breaking in a reaction. A reaction that favors one direction over another is called a regioselective reaction. In this reaction, the new bond to hydrogen can be formed at either carbon of the alkene. The two possibilities are shown here. Alkene addition reactions that form carbocations are regioselective for the product that comes from the more stable carbocation. In this example, the tertiary carbocation intermediate is more stable than the primary carbocation intermediate and will be formed in greater quantities. This leads to more of the product that results from the chloride attacking the tertiary carbocation. The steps that we took are generally applicable to all reactions, and it will be useful if you can find a systematic approach for tackling all predict the product problems. But before we can generalize such an approach, we need to consider one more facet of organic reactions, the concept of stereochemistry. Stereochemistry deals with the spatial, three-dimensional characteristics of a reaction. Alkenes, in particular, are subject to stereochemical consequences in their reactions because pi bonds have two faces, both of which can be involved in a reaction. For our example here, the pi bond can actually attack the proton from either of its faces. Let's view our alkene from a different perspective. Here we can see that the proton can add to the top face of the alkene or to the bottom face of the alkene. Once the carbocation is formed, the chloride can attack either the top face or the bottom face. In both of these instances, however, we form the same product. Let's look at an example in which this is not the case. In this example, we react a different alkene with hydrochloric acid. If we were approaching this problem from scratch, we would identify the functional group, recall how it reacts with the reagent, and think about any regiochemical preferences. We should also take into account any stereochemical consequences of the reaction. To do so, let's rotate our alkene again so we can better see both faces. Once again, we can see that the proton can add to the top face of the alkene or to the bottom face of the alkene. Once the carbocation is formed, the chloride can also attack either the top face or the bottom face. Now, however, we can see that the two possibilities are not identical. Notice that were these two products to be superimposed on top of each other, the ethyl and the isopropyl groups would not line up. These two non-identical products are called stereoisomers because they have the same connectivity of atoms but a different arrangement of the atoms in space. Don't worry if you've not covered the concept of stereoisomers yet in your class. Just note that the two resulting structures are definitely different compounds. Incidentally, both stereoisomers would be formed in the same amounts because neither the top nor the bottom face of the carbocation presents a more or less favored approach for the chloride ion. The main purpose of this tutorial is to show you that different products can result from any given reaction. These different products arise from either regiochemical or stereochemical factors that present themselves during the mechanism of a reaction. Thus, it is very important that you understand the mechanisms of the reactions that you will encounter in this course. They hold the key to predicting the products of your reactions. The following skill-building exercises will help you to practice regiochemistry and stereochemistry in approaching these types of problems.